think largely at present that's just a recognising the options. I can't remember whether the actual details have gone into 4.5 or whether they're going into 4.6.
There's also support for A5.
There is, but Cortex-A5 is just another architecture V7 chip.
Right,
So
I'm sorry, I thought was
yes.
a question about architectures or was a question about SoCs?
SoC.
Because I think, so for example, an obvious question is there Scorpion optimization? And the answer is no.
Okay. Let me answer slightly differently. The performance tuning that Roman has done for the A9 for a slightly out of order core do prove to be beneficial on other out of order cores. So it's always worth trying those A9 tuning on your hardware.
Yes, we had a slightly embarrassing situation early last year that if you tuned for Cortex A8, your code ran faster on an ARM9 than if you tuned it for Cortex A9. That is now fixed, I believe.
Depends on what benchmarks you choose.
When you look at the architectural licensees, though, I mean the game is sort of try it with the A8 scheduler, try it with the A9 scheduler, try it with the A9 scheduler and some funny options. You know,
pick the best one.
And sort of see what works. It's not totally intuitive, I guess.
Well, yes, one of the goals that we've got this year is to try and make this more scientific. So tuning for A9 really should be getting close to the best code for A9.
Sorry, no, I don't think. I mean, I wasn't tuning for A9. It's more if you're tuning for a Marvell core, you're tuning for a.
Indeed, yes.
So is it in the hands of the individual silicon partners to push forward microarchitectural optimization for their own SoC, or will ARM help with that?
I'm trying to put in place a fairly generic infrastructure in the compiler to allow people to write or just sort of plug in numbers for their core. It's never going to be quite as simple as that because there will always be features in the microarchitecture that requires some new underlying infrastructure. But my goal is to try and make this so that you do it once through a costing interface and extend the costing interface rather than go and tweak the code in a load of places and say, if it's this core, do this. The right way to do this in the compiler is say, what's the cost of doing A versus what's the cost of doing B? Right, on this core, that answer is A is 5 and B is 4, so I'll choose the one that's 4.
All right, thanks.
Right, as for 4.6, well, I've already mentioned sort of 3 of those items. Of course, there's always more work we can do on Neon. Neon's quite a big beast. The vectorizer in GCC is still relatively primitive, and we've got quite a lot of work to do on enhancing that. Just to show that this isn't all just smoke, and we do actually try to put some science behind it. I've been tracking code size in GCC for the last 4 years, very nearly now. This chart is quite confusing because unfortunately GNU plot doesn't separate out the key quite as I would like it. But it's showing essentially 3 builds of each of 4 architecture variations. So the red plot is ARM code at O-space, O2 and O3. So obviously you're seeing a trade-off there of size versus presumably performance. I don't have any actual performance numbers for these particular builds on this chart. But in general you can see that certainly at O-space code is coming fairly uniformly down. The caveat here, these are of course based off nightly builds of trunk. So occasionally you see anomalies, including a spike about 6 months ago, no, probably near a year ago now, where there was a sudden large drop in code size. Don't believe that one, it was a buggy compiler. But I've not taken out the numbers. Essentially it was throwing away important bits of the image. It's a very good compiler for saving code size, it's not a very good one for accuracy. The other thing you'll notice from this is the relative sizes of different architectural combinations. So adding VFP to your instruction mix actually saves you quite a lot of code size. The sort of slightly purple line on this projection is the VFP with ARM. Then you've got the thumb code, which is the green line, and then right at the bottom you've got thumb 2. Now those thumb 2 numbers are without VFP, so if you were to combine the sort of savings that we're seeing at the top with VFP to the thumb 2 image, you get an even better saving on this particular set of benchmarks.
So is this soft code ABI?
This is all soft float ABI, yes. I believe so.
Is it a single program which has a lot of internal calls, or is it
It's a collection of benchmarks. It's one of them is a lobotomized version of the Linux kernel, which is designed to compile on a lot of architectures without tweaking and reconfiguring. Essentially, all the ASM stubs were turned out into empty NOT type operations. There's a number of other benchmarks in there. I forget now the full list that's in Chiba. Can you remember? Can you remember what's in Chiba?
What?
The Chiba benchmark, the code size benchmark.
Oh, Chiba. No.
It's about 10 different applications that have been taken and are compiled with, set up essentially to compile on a number of architectures. It was the University of Szeged in Hungary that did this work as part of the PhD project. But it's a useful collection of things for just measuring size on.
So what I'm wondering is whether it's useful to turn on BFP just in a soft FP case, or whether the real benefit in going to BFP is...
No, well, these numbers are the soft FP case. So in terms of code size, you do benefit by turning it on.
Is that the benefit we're seeing here, or is it the benefit of moving from half float non-BFP to half float?
Try and point it out. Sorry for those who are on the video. The red lines are ARM with no VFP. These purpley lines are ARM with VFP. So that's the saving you would get from turning on VFP in terms of code size. This one at the bottom, the thumb 2 blue lines, are thumb 2 without VFP at all. Now, I haven't done a measurement, but my belief is fairly strong, and I think probably justified, that adding VFP to that mix is only going to improve things.
Where's that improvement coming from with VFP?
Essentially, when you're doing soft float, you end up doing a lot of library calls for each instruction. And essentially, you've got a library call now for each VFP instruction. Probably more, because you can't actually merge those instructions together as you could with the VFP unit. So every add now is a move everything into integer, move everything into R0, R1, call a value, now move those values back to somewhere else. And this gets quite expensive when you consider that you've also covered several other registers as well by making the call. So you get a lot more spilling happening in the compiler as well. Minutils was starting to get into the smaller. What's going on there? Smaller things. Most of this year has been fixing minor bugs, little problems with assembly, little problems with the linker, trying to get the ABI client compliance a bit better. Some of the attributes were in need of a bit of an update and overhaul. We're starting to work through a list. We have the team in ARM that's been looking at compatibility between our assembler and the commercial one. With GAS and the commercial assembler, to make sure that we're fully supporting unified syntax. And we probably have a list of about 50 minor deviations. Most of these don't affect most people because they are about not failure to give warnings and things like that when you've done things which are not technically supported by the architecture. So if you've written valid assembly, you've not got a problem. If you've written invalid assembly, GAS might not warn you about it. Since the assembler is largely used for compiling or assembling GCC generated output, I hope we're never going to fall into that latter category. There's a number of additions that we've done with the code source tree. They've added support for M4. which is largely actually just recognising existing instructions in the M profile architecture. Google have started and are making quite good progress on a gold port. That will be of benefit longer term because it should reduce link times. What we're doing for time. Debug. Finally, GDB now actually enables you to see the VFP registers when you're doing native debug. That's always been a bit of a bugbear of mine. Nobody's had time to go and actually fix it. Though it did require some kernel support to be added first, so it wasn't entirely our fault. We've also, I hope, now sorted out single stepping in Thumb2. A number of minor bugs there that were causing the debugger to suddenly lose track of where it had got to, and you could end up.
Which version of GDB does that support land in?
I think some of them are only in trunk and will be in the next major release.
Quite a few.
The Ubuntu stuff has largely got backports of most of the critical cases there, though. Is that right? Yeah. We've been quite careful to try and notify Doco when those have been detected. We've also got support coming for hardware watch points. It's sort of held up by the fact that the kernel doesn't support it. But the work that Will has been doing is sort of starting to make that a lot easier and nearer to being available. I think we're still waiting for some kernel patches to go upstream before that can actually be rolled into GDB, because I have to extend things like the ptrace interface.
On the debugger, the debugger currently knows about 3 out of the 4 instruction sets that the ARM chips support. Is there any chance of getting support
3 out
for
of
the
4?
DBX, Gisela? Well, we know the instruction set because it's Java bytecode.
Yeah.
We don't know the ABI without NDAs, so hence it's not actually in the debugger.
Yeah.
Is there any chance of getting that released now that it's perhaps commercially less important?
I shall have to pass that one up to management.
Describing me as management, really good.
That wasn't a compliment.
No, I know exactly. Let's have a chat, and I'll take away. It's a valid point you raised.
Currently, GDB dies if it.
No, I can see where you're coming from.
I think historically there were reasons why we couldn't. Miscellaneous tidbits. Valgrind support is coming. We're at the stage now where it supports ARM v5 in ARM state. Though somewhat surprisingly, you have to run it under a v7 machine. Don't ask me why. I don't know. Libraries. Well, I've written some optimized string routines. They're probably 3 times as fast as C code. Those are currently in a library called ULib, but they're under a BSD license. They really need importing into eglibc. We're working on the copyright agreement to sort of get that all sorted. Final thing really I want to mention is perf tools. Will's done some sterling work on getting that all sorted. I'm not going to go into the details now. If you want to know more, go to Will's talk session after lunch.
Shameless plug.
Indeed, yes. I think that's about it actually. I seem to have got through that faster than I expected. So, questions?
I noticed there's no LLVM work that was listed out.
LLVM is something that we're sort of tracking but haven't actually started any program of work on at this stage. It's a tricky one because working with Apple is not always that easy for anyone.
Well, working on the GNU toolchain, It's not that easy either.
It has different problems. The problem with LLVM is you can do a whole load of work and then Apple will do another drop of their code base and it will break everything you've just spent the last 6 months doing.
Yeah.
That's not really very good for managing an engineering team.
Right.
But we are keeping an eye on it, and certainly it is potentially important to the community. And some of the results that it's showing are actually quite good in some areas. Sometimes it can do a lot better than GCC. So it shows that GCC has got a way to go in certain areas. I don't want to get into the politics today of whether this is the right way to go in the future or not. Yes.
I have a question on the use of the tool, cross-compile versus native. My job is to produce kernels for the Ubuntu distribution, and all of my engineers use code sorcery to test the compiles, but the actual kernel that goes into the archive is built under GCC on a native platform.
Yeah.
Have you ever noticed differences between the outputs, I guess? They shouldn't be.
Can I take a crack at it?
Yes, sure.
So I think, there are two classes of differences I would expect that you might see, and one of them is a bug and one of them is not. So the bug is if an identical compiler, same source code, same configuration options, is generating different code, native versus cross. There have historically been cases where that was true in GCC. That is sort of by definition a bug, but because of the way GCC's configure scripts and so forth work, it's possible, it's a relatively easy trap to find that something gets a little different native than cross. I think the biggest thing that you'll see when using our tools versus using what Doco is preparing for the actual distribution is just, it's a somewhat different collection of patches and such. So I mean, for example, the release that we just did in the spring, our 4.4 release, this is where version numbers get confusing. It's a 4.4 release, although it's really got in many ways the ARM backend of 4.5 and even some bits of 4.6. So depending how you look at it, it's one way to look at it is that it's 4.4. That's sort of the front and middle end view. The back end view is it's maybe sort of 4.5 plus.
Okay.
So there you certainly see some differences relative to a more FSF 4.4 looking native toolchain.
So Matthias is producing a cross-compiler package for ARM? Is that what I heard?
We do have cross-compiler packages, and but we will talk this week how to provide them in the DBA. So currently these are somewhat experimental builds, and you can install them on top of Lucid, but they are not, well, yet publicly available.
Why?
I can drop you an URL, and we don't build them on a regular basis as well. So,
but it doesn't need to be built manually, which is a big problem.
Yeah.
And we have various changes to do so that the packaging is also closer.
Okay. I'd just like a more integrated solution than what we're doing with sorcery.
So our goal is to provide both native and cross-compilers built from the very same source, so that we don't have this kind of divergences anymore.
I'm good with that.
And there's one other thing which is maybe not relevant for kernel builds, but we end up with different runtime libraries if you build cross-compilers or native compilers. So you don't have a full lit std++ if you build cross versus if you build natively. So
well, that depends on how you build it.
Maybe.
So there's no reason that a cross compiler doesn't have the identical set of libraries that you would get native inherently, unless you're doing something like a profile-directed feedback loop during your build process.
Right, but there are some link time tests done.
Correct. And if you get them right, you get the same bits. But yes, so one of the things is that building GCC, building any of the toolchain components in and of itself is not too hard native and not even too hard cross. assembling a complete cross tool chain and getting all those sorts of details right as if they're it's non-trivial.
You have very good documentation on that in your GDPC tree. The readme course or something is a really good way for someone who wants to do that. But we'd like to solve the problem and implement it for everybody. One question on the cross-compile quality. So what I want about, you mentioned there are old bugs when the cross-compile output is different from the native compiler, and I agree. The question is that frequent?
It's gotten much less frequent. It's something, I mean, so, you know, this is sort of like, you know, there were a fairly large class of cases where cross compilers from different host systems would result in different output too. You know, a Windows to ARM Linux cross compiler would do something different from a Linux to ARM Linux cross, you know, x86 Linux to ARM Linux cross compiler.
And versus 64 host.
Yes, that's right. So, you know, over the years, the number of such cases has gone down. But I mean, one of the things that we actually have some internal technology for is to actually validate that. And that's an example of the sort of thing that most people just don't do. Most people take the source code, they build it, and they have a compiler. It seems to work. They're okay. To actually ensure that your Windows hosts and your Linux hosts and your native compilers are all sort of, you know, matching up requires some science.
We used to recommend native building for production code, for production binaries.
Sorry, say that again?
Would you still recommend native building for production binaries?
No. No. If it were, I mean, I understand that personally, no. I mean, I understand why it's convenient and why in the context of something like Ubuntu, that's historically been the way that it's been done. I mean, you know, certainly if you're on an x86 system, it's a fair amount of sense. But if it was me, I would have a big rack of servers and I'd cross-compile. It's way faster.
Oh, yeah. But the difficulty isn't in the compilers,
it's not in the package.
That's right. I mean, one of my historical bugbears in Linux packaging is that there are of course a fair number of packages that don't cross-compile, and it's not about the compiler; it's about the packages.
That's clear.
Actually, it's about autocomp.
Well, yeah, I mean, whatever it's about, but it's about something.
No,
and it's
really about autocomp. Autocomp is actually pretty well. Anyway, I don't think we want to go in that direction.
But I mean, I think the answer to your question is I would native compile. I mean, I would cross-compile whatever I could cross-compile.
In the past, one bug I've seen in cross-compiling versus native compiling has specifically been floating point constants ending up different when a native compiler versus a cross-compiler, especially on ARM.
I believe that issue has been resolved for a bit, but I do know exactly the sort of thing you mean.
The most common one these days is actually 64-bit hosts generating slightly different code because of the way the GCC internally handles integers. It's relatively uncommon now, but it can still occasionally happen.
So what was the effort proportion within ARM for developing GCC versus ARM CC?
Sorry, I didn't quite catch the...
What's the effort distribution within ARM?
What's the relative size of the two teams?
Well, today ARM CC team, actually it's the ARM Commercial Tools team. If you added everybody up, there's the compiler team, which is about 15 people, but then you've got a debugger team as well, and that's another 7 or 8 people. So they're probably sort of between 20 and 30 people working in that area, and at present I've got about half a dozen working on tools.
Okay, so those are totally separate teams?
Yes.
As they would have to be, right?
Yes, well, we do talk to each other on areas where we can talk to each other, and several members of my team are former members. I'm a former member of the commercial compiler team. That's where I was before 2008 when I moved over. I had quite a difficult juggling act in the past because I was working in the commercial compiler team and yet still doing some maintenance of GCC.
But are those still in competition within ARM? Because I guess that GCC might be removing some revenue opportunity from the commercial GCC. CC?
I think the honest answer is not really. There are still some people who don't really understand the differences and the commercial needs. We have to support GCC these days, so we have to support the open source community, and it's just not practical to do that with ARMCC in some circumstances. There are some circumstances where it's still possible. It is now largely possible to build, I think ARMCC has been recently used to build about 80% of Debian.
So
It's quite a large proportion of the packages, but there are still a large number of packages which still won't go through it, simply because they're doing things like using inline assembler, which is quite difficult to actually support in a compiler that isn't GCC.
So, as this is an open meeting, and I want to be completely explicit about this because it's an important point. As Richard says, we've been building the open source tool side within ARM. We're ramping it further. So, we have moved to a position where both the open source tools, which are very important to us, and our commercial tools, which are very important to us, are on an equal footing, and we want to add support for our IP as we create it at the same time in both tools. And you've seen that with the A9 tuning is handled about the same time in both tools. From how do these two things balance out commercially, we, like other large, monolithic silicon vendors, also, we do cross-compilation in our commercial tools, and for some people that's a good answer. We also provide profilers and other tools and JTAG-based development. But we are trying to improve our effort and invest on the open source side. It is important to us. So we've resolved our internal conflict of interest. We understand that we're trying to do our best.
Just out of interest, when you're sort of applying one set of optimizations to one of those code bases, can you at a high level use the same philosophy, the same?
Ramon?
Probably not, because some of those optimization passes might be very different between the two compilers, and it's hard for us to go and look at what ARMCC does. We don't have access to their source base, and they also wouldn't look at GCC because of IP pollution reasons. What we would talk about is microarchitectural variations, or is this heuristic good to try out, and those kinds of across the board set of parameters. So it would be at a meta level rather than in-depth compiler optimization related discussions.
One of the key things in GCC is that, and I actually think that this has been taken too far, but that it tries to sort of avoid knowing what architecture it's compiling for as long as possible. And the optimizers do various things that are sort of, this is just good no matter what machine I'm on. And then after a while you sort of go, I have to face reality. I'm dealing with the chip at hand, and so I've got to start compensating. I've never seen the ARM compiler code base, but most architecture-specific compilers start making those decisions much earlier. And I actually think GCC probably needs to grow some of that, not necessarily in a terribly algorithmic way, but your optimizations that are doing loop unrolling ought to have some idea of just how much unrolling makes sense on the architecture that you're on, given the body of the loop and so forth.
Yes, I mean there are some passes which do actually take some of that information into account. The vectorizer, I think, looks at some costs to decide whether it's worth trying to vectorize a loop, whether it's likely to end up beneficial or not. There are other passes which are rabidly against trying to make those decisions, and quite often they end up doing the wrong thing. Conditional execution is another area where actually you want to try and decide early on whether you're going to try and do this or not.
On a related topic, QEMU has become quite a useful tool for development, and I've been using it a lot for the work that I'm doing. Has ARM been working with QEMU or doing any development?
Well, I would go to Mark, actually, yeah. So Code Sorcerer has been doing some work around QEMU, trying to pull together the A9 multi-core support.
Yeah, so I mean, we've done a collection of things, both, well, I won't air all the dirty laundry here. We did a bunch of things for ARM V6 and V7 that for a while we had to keep to ourselves.
Yeah, I remember that.
And then since that stuff went out with Dave's help, then we've had some follow-on projects directly with ARM to add more features. And there's a set of things that we're doing for our own, internal purposes or on behalf of other clients as well. So I absolutely agree. I think QEMU is a very important tool, and it's one of these things that's sitting on the edge of being used by exponentially more people than it is currently being used by. So right now I think the set of people that are sort of using it on a routine basis are sort of like this, and it's going to go like this very quickly.
What worries me with QEMU is the fragmentation. So there's an awful lot of patches for this board and that board and another board, and they're not in the main code base.
That's right.
So it's really quite hard to pull one and build it for several platforms and version skew and stuff. And
that might be a kind of upstream merging issue that QEMU seems to have a special case of.
Well, I think there's a combination of upstream sociology and sort of commercial pressures. I mean, this is I think to some extent people used to see the same thing around UC Linux, that there's a set of things where people have a really good stake in getting them upstream because they want them to live for a long time, and there's a set of things where they're trying to solve a short-term problem and they're much less motivated to get them upstream. And I think some of the QEMU activity has been in that latter.
It's upstream doesn't always take specifically on patches for QEMU. Well, upstream for QEMU doesn't like taking patches at all.
Who could that be?
So there's an interesting conversation there for another day, another time.
Would it be worth talking? Go ahead.
Sure.
No, go ahead.
I was going to ask, would it be worth talking about what the difference is between code sorcery branches versus GCC branches, and and what the use cases are for each of them? Why people should consider them in different contexts?
Well, so I was hoping there's this toolchain selection thing this afternoon, and I was hoping maybe to have a bit of that conversation.
Just have a high level of what the difference is in strategy between them.
Right.
I don't have a specific answer to that one at the minute. I think probably we should have a conversation with Mark said after lunch.
All right.
We appear to be out of time.
That's right.
Are we out of time?
Yeah.
There you go. The session has ended. Right.
Very nice.